A-level maths can throw some peculiar equations at you, maybe taking concepts that you're already familiar with and then twisting them in a further way that you'll be expected to deal with. Implicit differentiation is one such example of such a topic. Let's say you had just been given this curve here of y equals 2x squared plus 5x minus 7, and you wanted to find an expression for the gradient of any given point on this curve. Well, you would differentiate, wherein you would times the coefficient and the power to make 4, and then drop the power by 1 to make that just x on its own. The 5x just becomes 5, and the minus 7 disappears. You can then just plug in that x value, and you'll get what the gradient is. What if, however, you had been given this, where you have y squared minus 3y equals x cubed plus 8. We now have multiple y terms on the left-hand side. And in fact, as we go forward, we may even have y terms times by the x on the same side. How are we expected to use differentiation in the same way if we also want the gradient of this curve? Well, what we're going to do is we are going to differentiate both sides using the same usual methods, in that on the right-hand side this would just become 3x squared. And on the left here, we will use the same principle in that you've got a coefficient times a power, so that's 1 times 2, which will just be 2, y, and the power will drop to 1. And over here, this minus 3y will just become minus 3. However, what we're also going to write is a dy over dx next to these terms. So, you will differentiate a y the exact same way that you differentiate an x, only you put a differential symbol afterwards. Now, the reason for this is that this is actually exactly what happens when we differentiate y usually. Strictly speaking, whenever you differentiate a y, it just becomes a dy, and whenever you differentiate the x's, it becomes dx. So really here, when this differentiates, y would just differentiate to 1, and it's one lot of dy because we have changed with respect to y, and then that equals the 4x dx plus 5 dx, because we have now changed with respect to x on this side. It's just what we then do in a single step without thinking about it, is then divide the dx onto the other side. So you've got one lot, so that doesn't make a difference, so you just end up with dy over dx, and here you're then left as before with the 4x plus 5 on its own. Here, this would be 3x squared dx, and this would just be 2y dy minus 3 dy. It's just now we're going to divide everything by dx to get the 3x squared on its own, as we would usually expect it to look. Now that we're at this stage, we can factorize out the dy over dx as a common factor to get it as a single differential, leaving us inside here with 2y minus 3 equals 3x squared. And so we can say that dy over dx on its own is equal to 3x squared over 2y minus 3. This is now the equation that would get you the gradient at any given point, and it's an equation that will require you to put in both the x coordinate and the y coordinate, whereas usually you would just need the x coordinate. Of course, because with differentiation we can then have more complex terms to differentiate that require a few different rules, we can now add that extra level of complexity to implicit differentiation as well. So over here, we're not only going to be looking at differentiating e term, but we're also going to be looking at differentiating something with two variables times together. This is going to require the product rule. Of course, I'll just be going over the basics here as I go through the working, but if you want a more thorough explanation of the product rule or the quotient rule or any of the other special rules, there are other videos on those that you can look into as well. Here though, to start off with, if we were to differentiate this first term, because it's two things times together, each of which have a variable, and they can't be simplified into a single term, what we'll have to say is I have to label one of them u, I'll make that the y, and then one of them will be v, that will be the e to the minus 2x. If we then differentiate each of these individually, y is just going to become an individual dy over dx, so 1 times dy over dx, and the differential of e to the minus 2x, you're going to have minus 2e to the minus 2x, because you multiply by the differential of the power and then keep the e term the exact same. For the product rule then, you do your differential of u times your regular v, add the regular u times the differential of v, so that it becomes e to the minus 2x dy over dx, so this times this, then add the y times the minus 2e to the 2x, so actually we might as well make that a minus straight away, so minus 2y e to the minus 2x, and then this will equal on the other side just the regular for the 2x will be the regular differentiation, so that just becomes 2, and then here y squared would become 2y dy over dx. From this stage, we're going to want to bring the dy's over dx's onto the same side, and everything that doesn't have it onto the other side. So this could become e to the minus 2x dy over dx minus 2y dy over dx equals 2, and if this is a negative over here, it's going to become a plus, so plus 2y to the minus 2x. As before, we'll now bring the dy over dx together by factorising, so dy over dx in brackets of e to the minus 2x minus 2y equals to 2 plus 2y e to the minus 2x. Therefore, your dy over dx is going to equal 2 plus 2y e to the minus 2x all over e to the minus 2x minus 2y. With this as our equation for our gradient, therefore, we can say find the point P, the point P on the curve has coordinates 0, 1, find the normal at P in the form of ax plus by plus c equals 0. Well, if we're going to be working out a normal, which is a straight line, so a y equals mx plus c, we're going to need the gradient. And to get the gradient of the normal, you need the gradient of the tangent. So for the gradient of the tangent, we can just take this gradient expression here, and then make the x coordinates 0 and the y coordinates 1. So that'll be 2 plus 2 lots of 1, then e to the minus 2, 0, and then underneath here, e to the power of minus 2 times 0 minus 2 times 1. Together, this is going to get you 4 over minus 1, which is just minus 4. Therefore, the gradient of the normal is going to be quarter, because it's a negative reciprocal. Change the sign and make it 1 over. Now just plugging values into a y equals mx plus c. We know the y is 1, the m is therefore the quarter, the x is a 0, and there's a plus c. So 1 equals, a quarter times 0 is just 0, so 0 plus c, therefore c has to equal 1, therefore y equals a quarter x plus 1. But this is in that form. We need to get the y onto the same side as the other two terms, and we need to make them all integers, ideally. So, because this is a quarter, we can times that by 4. If you times a quarter by 4, that's just going to leave you 1, so a single x. Here, with minus the y over, and now times it by 4, so it's minus 4y, and then this is going to become plus 4 at the end here. So, if we can see the difference with this implicit differentiation, where we're just treating the y's exactly like we would if there was an x, only we're going to write a dy over dx after it, and then we'll bring those terms onto the same side. Then we'll factorise the dy over dx out, leaving and thus with another factor that we can just divide by, to leave the dy over dx on its own. If we're good with that, let's just see how you can get along with an example of your own. Let's just say that you were given cos 2x plus cos 3y equals 1, where the x is going to be between minus pi over 4 and pi over 4, and then the y is going to be between 0 and pi over 6. Find dy over dx, and then point P has an x coordinate of pi over 6. Therefore, find the y of P, and then lastly find the normal at P. So you may wish to consider how we are going to differentiate the trigonomic functions. Maybe remind yourself just of those techniques if you're not familiar with them already. Think through each of the different stages that we're going to need, what information you have, how you can then use that to get your answer. Pause the video, have a go for yourself, and then press play again when you're ready to compare. So, to start off with, if we are going to be differentiating these expressions, well, the cos 2x, well, cos differentiates to minus sine, but also, just like we had with the e term, you're going to times by the differential of this bracket. So the differential is 2, so this is going to become minus 2 sine 2x. This cos here is going to go through pretty much the exact same treatment, and we're going to get minus 3 sine 3y, but that's then going to have a dy over dx times by it afterwards, and then the 1 is just going to disappear as 0. From here, we could then add the 2 sine 2x over, so you have minus 3 sine 3y, dy over dx equals 2 sine 2x, and then divide by this to leave the dy over dx on its own, thus it equals 2 sine 2x over minus 3 sine 3y. Next, now that we have that the point P has the x coordinate of pi over 6, find the y of P. Well, if we were to plug in that cos of 2 times pi over 6, so we're going to want to make sure that we're in radians here, plus cos of 3y equals 1. Rearranging, we're going to get that cos of 3y will equal a half. So 3y will equal the cos inverse of a half, which would be a third pi. Therefore, y will equal a ninth pi, which is indeed within the range of y values we were expecting or looking for. If this hadn't have been within that range, we would have had to have found an equivalent value somewhere on the cos graph. If you want to look up how to do that, you can look into how to solve for angles within a range in trigonometry. Lastly, now that we have the y value, we can go about working out the normal at P. So we'll first of all, as before, need to get the tangent. So we can say that the gradient of the tangent is going to be 2 sine of 2 times the pi over 6 over minus 3 sine 3 times a ninth of pi. Together, this is going to get you minus 2 over 3. Therefore, the gradient of the normal is going to be 3 over 2. Using our y coordinates and an x coordinate, you've got a ninth of pi equals 3 over 2 lots of your x coordinate, which was your pi 6 plus c. From here, therefore, you can work out that c has to be minus 5 over 36 pi. So usually at this stage we could say that y equals 3 over 2x minus 5 over 36 pi. However, because we're probably going to want them in integers in case it did ask, we can also just times up by 36 here, and maybe even also bring everything on the same side. So 3 over 2 times 36 is going to end up with 54x. then we're going to minus 36y over, and then this is still minus 5 pi here, 0 equaling. Okay. If we're good with that, we can see what we've done and we're happy with it. Let's just wrap up with one further question. So we have here this diagram which is showing us the curve of x squared minus 2xy plus 3y squared equals 50. And because we have both x's and y's in there, you end up with this curve looping back on itself between these lines here, where then we have the point Q and the point P. And we want to show, first of all, that the differential can be made using this equation. Okay, so if we just differentiate each term one at a time, the 2x squared is going to become 2x. Here, because this is a product rule, we're just going to want to think of this at the side. So we could think of it as u being minus 2x and v being the y. So the differential of u is just going to be minus 2, and the differential of v is just going to be dy over dx. So together, if we're doing our u dash v and uv dash, you end up with minus 2y minus 2x dx. Then here, this is going to become plus 6y over dy dx, and then the 50 is going to disappear as a 0. Move the things that don't have the dy over dx in them to the other side. So you have, well, what is essentially 6y dy over dx minus 2x dy over dx, just to get it in the order of the y followed by the x of the other side, of the answer. And over here, this is like 2y minus 2x. Factorize out the dy over dx to leave you with the 6y minus the 2x equals 2y over 2x. So dy over dx on its own is going to be 2y minus 2x over 6y minus 2x. And here we can cancel through by a factor of 4, leaving us with just that y minus x over 3y minus x that we had to show. Next, the curve is used to model the shape of a cycle track with both x and y measured in kilometers. The points P and Q represent the furthest west and the furthest east from the origin, and therefore using this part A, find the exact coordinates of P. Well, usually you wouldn't be using the gradient to find a coordinate necessarily if it wasn't your usual maximum or a minimum. But this is a kind of maximum minimum in a way. With your usual, so your maximum point, something like this, or your minimum point, something like this. So on the diagram, that would be something like here, or here. You'd be looking for where the gradient is 0. Here, though, at P and Q, this, because they're where it's a straight vertical line, these would have an infinite gradient. How can you get a value of infinity from a fraction? Well, you get that when the denominator is 0, because you can't divide by 0, it's undefined. Therefore, regardless of what the top would therefore become, we'll get P and Q if we say that 3y minus x in the gradient expression equals 0. But that's not good enough, because we still just have these two unknowns here. A half, so 3y will equal the cos inverse of a half, which would be a third pi. Therefore, y will equal a ninth pi, which is indeed within the range of y values we were expecting or looking for. If this hadn't have been within that range, we would have had to have found an equivalent value somewhere on the cos graph. If you want to look up how to do that, you can look into how to solve for angles within a range in trigonometry. Lastly, now that we have the y value, we can go about working out the normal at P. So we'll first of all, as before, need to get the tangent. So we can say that the gradient of the tangent is going to be 2 sine of 2 times the pi over 6 over minus 3 sine 3 times 1/9 of pi, and then we'll square root it to get y is plus or minus 5√3/3. Plus or minus because you always have two answers to a square root. And this also makes sense here because we've got 2 points that have an infinite gradient. You're going to have 2 different y coordinates. Because we're specifically looking for the coordinates of P, we're going to take the negative because that's below the x-axis. And then if we know that y is going to be minus 5√3/3, we can work out x because that's just 3 times y. So x is therefore just going to be minus 5√3. So just reiterate, P is minus 5√3 and then minus 5√3/3. To wrap up with, explain briefly how you would find the coordinates of the point that is furthest north of the origin. And so you don't need to carry this out as calculations, we don't need to do these steps again. But the principle you'll be using is what I was mentioning before with the maximum and minimum. This furthest point north, which is what I've already done a dot here for, that is where the tangent will be a horizontal line when the gradient is 0. To make the gradient 0, the numerator has to be 0. So you'd set y equals x, and then you'd solve through, as you just have here, with them being the same number. One final thing, actually, I just want to mention, but because it hasn't come up in any of these questions here, but it is still something you may find. One of the less usual differential rules you have is if x is in the power. This will have also been mentioned elsewhere, but I'll just do it again here to start off with the x. If it's 2 to the power of x, then your differential is going to be 2x ln 2. So whatever this number here is, or in the original base, this term stays exactly the same, but then it gets times by the natural logarithm of that same number. Yet if instead you had had 2 to the y, as you may well do in these implicit differentiation questions, that would 2 to the y, because that stays the same, and ln 2, and don't forget your dy over dx, because it is a y term that you are differentiating. So yeah, there are many different ways that we can deal with y terms if we're having to differentiate, but ultimately they are the same techniques as we would be using with the x. You just need to put this dy over dx at the end.